2. 3-bisphosphoglyceric acid is a 3-carbon isomer of the glycolytic intermediate 1,3-bisphosphoglyceric acid. 2. 3-BPG is present in human red blood cells at approximately 5 mmol/L. It binds with greater affinity to deoxygenated hemoglobin than it does to oxygenated hemoglobin due to spatial changes. 2. 3-BPG fits in the deoxygenated hemoglobin configuration, but not as well in the oxygenated. It interacts with deoxygenated hemoglobin beta subunits by decreasing their affinity for oxygen, so it allosterically promotes the release of the remaining oxygen molecules bound to the hemoglobin, thus enhancing the ability of RBCs to release oxygen near tissues that need it most. 2. 3-BPG is thus an allosteric effector. Its function was discovered in 1967 by Reinhold Beneš and Ruth Beneš. Metabolism. 2. 3-BPG is formed from 1,3-BPG by the enzyme BPG mutase. It can then be broken down by 2,3-BPG phosphatase to form 3-phosphoglycerate. Its synthesis and breakdown are, therefore, a way around a step of glycolysis, with the net expense of 1 ATP per molecule of 2,3-BPG generated as the high-energy carboxylic acid phosphate mixed anhydride bond is cleaved by bisphosphoglycerate mutase. The normal glycolytic pathway generates 1,3-BPG, which may be dephosphorylated by phosphoglycerate kinase, generating ATP, or it may be shunted into the Lubering-Rapport pathway, where bisphosphoglycerate mutase catalyzes the transfer of a phosphoryl group from C1 to C2 of 1,3-BPG, giving 2,3-BPG. 2,3-BPG, the most concentrated organophosphate in the erythrocyte, forms 3-PG by the action of bisphosphoglycerate phosphatase. The concentration of 2,3-BPG varies inversely with the H+, which is inhibitory to catalytic action of bisphosphoglyceromutase. There is a delicate balance between the need to generate ATP to support energy requirements for cell metabolism and the need to maintain appropriate oxygenation, deoxygenation status of hemoglobin. This balance is maintained by isomerization of 1,3-BPG to 2,3-BPG, which enhances the deoxygenation of hemoglobin. Low pH inhibits the activity of biphosphoglyceromutase and activates bisphosphoglycerate phosphatase, which favors generation of ATP. Effects of binding. When 2,3-BPG binds to deoxyhemoglobin, it acts to stabilize the low oxygen affinity state of the oxygen carrier. It fits neatly into the cavity of the deoxy conformation, exploiting the molecular symmetry and positive polarity by forming salt bridges with lysine and histidine residues in the SS subunits of hemoglobin. The R state, with oxygen bound to a heme group, has a different conformation and does not allow this interaction. By itself, hemoglobin has sigmoid-like kinetics, which makes easier another subunit's binding. By selectively binding to deoxyhemoglobin, 2,3-BPG stabilizes the T-state conformation, making it harder for oxygen to bind hemoglobin and more likely to be released to adjacent tissues. 2,3-BPG is part of a feedback loop that can help prevent tissue hypoxia in conditions where it is most likely to occur. Conditions of low tissue oxygen concentration such as high-altitude airway obstruction or congestive heart failure will tend to cause RBCs to generate more 2,3-BPG in their effort to generate energy by allowing more oxygen to be released in tissues deprived of oxygen. Ultimately, this mechanism increases oxygen release from RBCs under circumstances where it is needed most. This release is potentiated by the Bohr effect in tissues with high energetic demands. Bohr effect is another useful way to solve the affinity problem of the hemoglobin, and it is related to the pH and the CO2. It's important to highlight that the behavior of myoglobin doesn't work in the same way, as 2,3-BPG has no effect on it. In pregnant women, there is a 30% increase in intracellular 2,3-BPG. This lowers the maternal hemoglobin affinity for oxygen, and therefore allows more oxygen to be offloaded to the fetus in the maternal uterine arteries. The fetus has a low sensitivity to 2,3-BPG, so its hemoglobin has a higher affinity for oxygen. Therefore, although the PO2 in the uterine arteries is low, the fetal umbilical arteries can still get oxygenated from them. Fetal hemoglobin. It is interesting to note that fetal hemoglobin exhibits a low affinity for 2,3-BPG, resulting in a higher binding affinity for oxygen. This increased oxygen binding affinity relative to that of adult hemoglobin is due to HbFs having 2-alpha, gamma dimers as opposed to the 2-alpha, beta dimers of HbA. The positive histidine residues of HbA beta subunits that are essential for forming the 2,3-BPG binding pocket are replaced by serine residues in HbF gamma subunits. Like that, histidine N143 gets lost, so 2,3-BPG has difficulties in linking to the fetal hemoglobin, and it looks like the pure hemoglobin. That's the way O2 flows from the mother to the fetus. As we can see in the following image, fetal hemoglobin has more affinity to oxygen than adult hemoglobin. Moreover, myoglobin has the highest affinity to oxygen. Differences between myoglobin, fetal hemoglobin, adult hemoglobin diseases related to 2,3-BPG. Hyperthyroidism. A 2004 study checked the effects of thyroid hormone on 2,3-BPG levels. The result was that the hyperthyroidism modulates in vivo 2,3-BPG content in erythrocytes by changes in the expression of phosphoglycerate mutase and 2,3-BPG synthase. This result shows that the increase in the 2,3-BPG content of erythrocytes observed in hyperthyroidism doesn't depend on any variation in the rate of circulating hemoglobin, but seems to be a direct consequence of the stimulating effect of thyroid hormones on erythrocyte glycolytic activity. Iron deficiency anemia. This illness is characterized by a lack of iron, and as 2,3-BPG needs this chemical element to be synthesized, BPG concentration decreases and hemoglobin binds tightly to oxygen. As a result, oxygen release to tissue is reduced. Chronic respiratory disease with hypoxia. Recently, scientists have found similarities between low amounts of 2,3-BPG with the occurrence of high-altitude pulmonary edema at high altitudes. Hemodialysis. In a 1998 study, erythrocyte 2,3-BPG concentration was analyzed during the hemodialysis process. The 2,3-BPG concentration was expressed relative to the hemoglobin tetramer concentration as the 2,3-BPG HB4 ratio. Physiologically, an increase in 2,3-BPG levels would be expected to counteract the hypoxia that is frequently observed in this process. Nevertheless, the results show a 2,3-BPG HB4 ratio decreased. This is due to the procedure itself. Mechanical stress on the erythrocytes is believed to cause the 2,3-BPG escape, which is then removed by hemodialysis. The concentrations of calcium, phosphate, creatinine, urea and albumin did not correlate significantly with the total change in 2,3-BPG HB4 ratio. However, the ratio sampled just before dialysis correlated significantly and positively with the total weekly dosage of erythropoietin given to the patients.